Hey, hello everybody. Hey, this is going to be a lecture on work, but we're going to graph some things, and we are going to talk about variable forces when it comes to work. Okay, so this is going to be week 8, lecture 2. So in week 8, lecture 1, I reviewed a bunch of the stuff from the lecture on the end of week 7 and went over some of the aspects of question of the day for 12.4 and our question of the day for 12.8. And that is all constant force. So I'm going to review that a little bit, and we'll talk about how it is on a variable force. All right. So if we have here work with a constant force. Okay, now this is a little bit redundant because this is what I talked about before in those lectures. And that is just going to be work is equal to force times distance. Okay, and again, we can talk about that cosine theta. We can talk about the dot product between those. But this is when you have a variable force. So if you have a variable force, and this will make sense if we graph this. Okay. So if we have a force, let's say it is in newtons, and then we have displacement in meters. Okay, and if we even take a look at the question of the day for 12.4 and 12.8, if we had a force of, let's say, 52 newtons, and now remember that 52 newtons was the 60 cosine 30, so that was the constant force, the one that was going in the same direction as displacement. And let's say that we went 5.4 meters, okay? And we started out at 0 meters. That is the same displacement that were in those questions of the day. And when you calculated the overall work done, it was equal to 280 joules, rounded, of course. Now, if we think about this, if we take the area of this rectangle, the area of that rectangle is in fact 280. We're just going to have 52 times 5.4, and that is going to work out, again, slightly rounding, to equal that. So we can now say that work is equal to the area of, or we can say under a force versus displacement graph. Okay, force difference displacement. So if we have a constant force, as in this case of 52 newtons, that is going to be just a simple length times width. And that's what we have. Now, the next thing we're going to talk about is a variable force, okay? And a variable, and there are lots of variable forces, okay? But the probably the easiest and the simple one to think about a variable force is that of a spring. Now, you guys can imagine that if you had a spring, okay, to stretch a spring, okay, it doesn't take much to stretch a spring, a little bit, all right? But the more that you stretch it, the more that the force goes up and up and up and up. So when you're out here, the force is much greater, okay? And if we think about that, when we stretch it a little bit, it's as just one of this coil gets stretched, and then we stretch it more, it's a second coil and a third coil and a fourth coil. So even though they're all actually stretching just a little bit as time goes on, if we just think about it going one coil at a time, we can see that one coil is the equivalent of a distance, and that our force is proportional to distance. Our force is proportional to distance. All right, we are going to come back to this, okay? But for a spring, force is proportional to displacement, or force is proportional to x. Okay, x would be a displacement in one direction. Okay, now there's something called Hooke's law, and that is F is equal to negative kx. All right, we can see here whenever you have a proportionality and you want to make it into an equal sign, that you would just add a constant. For example, if you increase a distance, let's say in miles, that would be, if you increase in miles, you're also increasing in kilometers, right? If you go 1 kilometer, you're going to go a certain number of miles. So kilometers, miles, you get more, you get more. So what is the proportionality constant? What is the proportionality constant between miles and kilometers? Okay, so there is, so we can say miles is proportional to kilometers, and for every 1 mile, that is equal to 1.6 kilometers. So this 1.6 is what is called a proportionality constant. And if we divide by 1.6, okay, then that constant, that proportionality constant would go to the other side, and they would be different. But that is what a proportionality constant is. So for Hooke's law, okay, F is equal to negative kx. And this is applicable for a spring. And a lot of things act as a spring. For example, if we take and we bend this meter stick, okay, the amount that it bends is proportional to its force. And so we can think of this, even though we're not really seeing it as a spring, we can view it as having a spring constant. And if we change it down by, let's say, 1 centimeter, it will have a proportionate amount of force to make it curve down. All right, now this negative here, okay, the K is never negative. The K is never negative, but the force is always going to be in the opposite direction. The force is always going to be the opposite direction of displacement. So it's either negative force is equal to K times X, or positive force is equal to K times negative X. And if, again, we look at the spring, okay, and we pull it down, okay, then there's more force, more distance. And I'm going to do a quick little experiment to show you guys this and on how to determine what that is. So with no weight on the spring, I'm going to measure this, and it is at 46 centimeters, 46 centimeters. Okay, we'll come back to that 46 centimeters. Now I'm going to take a force, and this is a half a kilogram, which means that when we multiply by 9.8, that's going to be the force of 4.9 newtons, 4.9 newtons. All right, so let's hook this up, and now we're going to see that stretched out, and now we're going to measure that, and that is at 62. That is at 62 centimeters. Okay, so now we're going to say F is equal to K delta X. Okay, how much did it change by? So we know our force is 4.9 newtons. Okay, remember that was mg, and now we're going to have K, and now our final position was 0.62 meters minus 0.46 meters. And we can do the math here, okay? We're going to do 0.62 minus 0.46, and we get 0.16. 0.16 K times 4.9 newtons. This is meters. Now we want to know, what is the K? So we're going to divide both sides by 0.16, and our K is going to equal to 30.6. Okay, 30.6. 30.6. Now, what are the units? That's going to be newtons per meter. Newtons per meter. And in the same way that we graphed this to calculate our force, we're going to make another graph. Okay. Now this time that is going to be equal to a variable force. So now again we have force and we have displacement. And we're going to start at 0, 0. So this time we're going to have a slope, okay? And this slope for a spring is equal to the K value, which is equal to 30.6. 30.6 newtons per meter, okay? Remember, that right there is the slope. That would be rise 30.6 divided by run, which would be 1 meter. Okay, so how much work was done when we stretched that from, let's say, 0 to 0.16 meters? Okay. So what is that area? Okay, and now we can see that this is a triangle, so the area is equal to 1/2 the base times the height. 1/2 the base times the height. So right here we know that the base is 0.16. Okay, so we can say 1/2 the base of 0.16. Now, how do we calculate this height? Okay, now if we think of this as y is equal to mx plus b, and we can see that y-intercept is just 0. So we want to calculate this height right here. That is going to be y is equal to, what is our slope? We said it was 30.6, and we know that our x is 0.16, and we can now say times 0.16, and that's going to be 4.9. So our y here is equal to 4.9. Now, we already knew that because that's how we figured it out, okay? But remember that y is the same thing as the height, which in this case is force. So now we're going to have 4.9, okay? And we're going to take that times 0.16 divided by 2, and that is 0.392. So 0.392 joules. Okay, and that would be equal to the work. But now I want to talk about having a formula that's going to give us work. Now remember, this m right here is kind of the equivalent of our k here, and this y is equal to the force. Now, how did we get this y value? How did we get this force? Well, we did k times x. So now what we can do here is we can have 1/2 of x, that was our base, times our height, which was kx. And now if we look at this, this is going to be 1/2 of k times x squared, 1/2 k x squared. And this is equal to the work done by a spring. Okay, so again, this is a variable. This is a variable force. And that is where we're going on this next little section for variable forces, and that would be for a spring. Now, to see where this can go in its application, to calculus. Now, again, if you're not in calculus, no big deal. We're not going to be using any of these integrals, but you guys are about to, at the after the end of the or start of the new year, you guys are going to be doing anti-differentiation, which you know is integral. So you into that. But let's say we have some curve like this, okay, where this is force and this is displacement, and we have some value. We can see that the work is going to be the force times the distance. But remember, in order to get this to be regular x, we need to take the integral, and this force has to be the force with respect to x. And now we can just get the area under the curve is going to equal this work. And that is the same thing that you're doing in calculus. When you do integration, you are just calculating the area under a curve. And that's where it's going to go. So we're going to go from simple, which is just going to be a constant force, which will give you the work. And then we're going to go to a variable force, but that is linear, which is going to be a spring. And these are the kind of secondary sorts of questions that make it a little bit trickier than the constant force. And we are not going to get into this as of yet, because you haven't had the math there. But when you take the integral of the force in the x direction times dx, and that would give you the overall force. So let's do another example here, and we'll see how much work we have if we add some work to this. So here I have another 500 gram mass, and I am going to add that. I'm going to add that to this, and now we're going to first predict. We're first going to predict what the stretch of that spring is, okay? And if we say F is equal to negative kx, and I would say for now, if you ignore that negative and just have the perspective of which way it's going to go, that might help so you don't get confused. Remember that k is never negative. So now we have a force of now 9.8, and that's going to equal to kx. And if we divide by our x, which remember was 30.6 newtons per meter times x. So this is 9.8 newtons. Now we're going to divide by 30.6 newtons per meter. Newtons will cancel out. The meter is in the denominator of the denominator, which means it's the same as the numerator. 9.8 divided by 30.6, and that is 32 centimeters, 32 centimeters. So what we are predicting here that this 32 centimeters, okay, sorry, that is 0.32 meters. That is what our stretch should be, okay? And remember that we started off at 0 at 44. So we're going to add 0.442. So 0.32 plus 0.44 is equal to 0.76. So now if we check and we measure from our base, the bottom of the spring should be at 0.76 centimeters. So now we're going to look here, and it is at 0.77. Okay, so pretty close. Given our our experimental error, that's pretty close. Now, let's talk about, hey, how much extra work? How much extra work did it take? How much extra work did it take to go from 0.16 to 0.32? Okay, so the work is going to be equal to 1/2 kx squared final minus x squared initial. So we can say 1/2 30.6 times 0.32 squared minus 0.16 squared, and 30.6 divided by 2 times 0.32 squared minus 0.16 squared. We need I need a parentheses there, and that's 1.17 joules. 1.17 joules. Now remember, we had only 0.39 joules. So if we think about how much work that is, okay, remember that when we subtract that, this is 0.32, we're going to end up in this section as a trapezoid, okay? So that can be a little bit tricky, but it's going to be the big triangle minus the little triangle. Okay, so there are some questions on problem set 2 that is dealing with this springs and our variable forces. Also, the area under the curve. The area under the curve is going to give you the amount of work done. So you may end up with a trapezoid, but it's just simply the area under the curve. All right, we will see you next time.